Welcome to our advanced deep dive into moving control volumes. Today, we're taking our core theoretical foundations and applying them to the pinnacle of aeronautical engineering, the jet engine. Note that all B citations refer to Appendix B of my upcoming book. We will move beyond basic conservation to a detailed, simplified analysis of jet engine performance. We'll derive equations for net thrust and analyze the thermal and propulsive efficiencies that define engine quality. I'm former Professor Ganesh from the University of Connecticut. Welcome back. Today we are diving into the fundamental conservation equations for a moving control volume, a cornerstone of fluid mechanics and thermodynamics. Why does this matter? Whether we are analyzing a jet engine in flight or a pulsating vessel, understanding how mass, momentum, and energy are conserved in a moving frame is essential for precision engineering. Today, we bridge that gap to moving systems. Our objective is to derive the general transport theorem and apply it to mass, momentum, and energy. We start with the Leibniz theorem. This mathematical foundation allows us to relate the rate of change of a property within a moving volume to the flux across its boundaries and its internal generation. Essentially, it tells us that the total change is the sum of what happens inside the volume plus what flows in or out due to the relative velocity between the fluid and the control surface. Applying this to mass, we see that for a fixed mass Lagrangian system, the rate of change is zero. However, for our moving Eulerian frame, we must account for the density flux across the surface. This leads us to the continuity equation. It's a simple yet powerful statement. Mass cannot be created or destroyed within our control volume. It can only be redistributed or transferred. Next, momentum. The rate of change of momentum within our control volume equals the sum of external forces acting on it, including pressure, friction, and body forces like gravity. For a jet engine, the net thrust is generated by the difference between the momentum leaving the nozzle and the momentum of the air entering the intake. This is the heart of propulsion. Finally, energy. We balance the rate of energy change within the volume with the work done by pressure and friction, plus the heat added through conduction or internal generation. This energy balance allows us to calculate thermal efficiency, how well we convert fuel into kinetic energy, and propulsive efficiency, how effectively that energy propels the aircraft forward. To recap, we've integrated mass, momentum, and energy conservation into a unified framework for moving systems. These equations are the tools you'll use to solve real-world aerospace challenges. In our next session, we will apply these principles to a detailed analysis of jet engine performance. Understanding the moving control volume is not just an academic exercise. It is the fundamental tool used to optimize the massive engines that power global commerce and travel. Today, we leave no term unexamined. Let's begin with the intake. As air enters the nacelle at velocity v, the momentum flux is simply the air mass flow rate, m.air, multiplied by that inlet velocity. This is our starting momentum for the engine system. In a moving frame of reference, this represents the inlet momentum drag, often called ram drag or F⁻RD. It's the momentum cost we must pay just to bring that air into our processing unit at flight speed. At the exit nozzle, we have the jet velocity V⁻J, but we must account for the mass of the fuel we've added. So the momentum flux leaving is the sum of the air and fuel mass flow rates, multiplied by that high exit velocity. While the fuel mass flow rate, m.fuel, is typically much smaller than the airflow, a rigorous conservation analysis requires its inclusion. This total exhaust momentum is the source of our primary propulsive force. By subtracting that entry momentum from the exit momentum, we arrive at the net thrust, F⁻N. This is the resultant force available to accelerate the aircraft or maintain its speed against atmospheric drag. It's essentially a balance. By adding energy, we've increased the momentum of the fluid as it passes through our control volume. The faster and denser that exhaust stream relative to the intake, the more thrust we produce. Engineers often break this down into components. Gross thrust, Fg, is what the nozzle produces, while ram drag FRD is the inlet penalty. Net thrust is simply the difference between these two opposing forces. But thrust alone doesn't tell us how good an engine is. For that, we need to analyze efficiency. How effectively are we converting energy into motion? Let's break down the propulsive and thermal components. The change in kinetic energy of the air as it passes through the engine is the energy we've invested. It is the difference between the exit and entry kinetic energy rates of the fluid stream. The power actually used to propel the aircraft is the useful work output. It is the product of the flight velocity v and our net thrust F subscript n. This represents the benefit we gain from our energy expenditure. Propulsive efficiency, ETA, is the ratio of that useful power to the total kinetic energy we added to the jet stream. It tells us what fraction of our energy investment actually moves the vehicle. This is known as the Froude equation for propulsive efficiency. When the jet velocity is nearly equal to the forward speed, the kinetic energy of the jet is utilized very efficiently, resulting in a propulsive efficiency that approaches unity, or 100%. At this point, the boundary quantity, which represents net thrust due to fluxes, becomes zero. Consequently, the rate of change of momentum is equal to the sum of the forces within the control volume. The acceleration of the mass, as stated in equation B.23, which refers to Appendix B equation 23 in my book, matches this sum of forces. Therefore, equation B.26 represents the generalized conservation of momentum equation. The key takeaway is that the rate of change of momentum for the jet engine airflow consists of a boundary flux term, net thrust, and the sum of the forces within the control volume, where thrust is generated by increasing the momentum of the flow through the engine. Therefore, what most engineers may not know is that both second and third laws of Newton are at play in jet propulsion. It's a dual application of classical mechanics in high-speed flow. Thermal efficiency, ETA, measures the conversion of chemical energy. It's the ratio of the added kinetic energy to the energy released from burning fuel, determined by its lower calorific value. Finally, the overall efficiency, ET, is the product of both. It's the ultimate measure of the engine's performance, relating the useful work done to the total energy we paid for in the fuel tank. Importantly, we see that overall efficiency is inversely proportional to specific fuel consumption, or SFC. To increase range and reduce cost, engineers strive to lower the fuel burned per unit of thrust. Similarly, the total energy equation, B.38, includes terms for heat conduction and viscous dissipation. Even in our simplified engine analysis, these fundamental balances are the ultimate source of truth. To bridge from these integral forms to the differential equations engineers use in design, we employ the Gauss divergence theorem. This allows us to convert surface fluxes into equivalent volumetric rates of change. This theorem is the mathematician's gift to the engineer. It's how we transition from observing the boundaries of our nacelle to understanding the complex gradients happening deep inside the engine core. We must also distinguish between types of derivatives. Equation B.29 relates the substantial derivative, which follows a moving mass, to the total and local derivatives within our fixed or moving control volume. It accounts for the relative flux across the boundary. The relative velocity is defined as vector u, the fluid velocity, minus vector v, the control volume velocity. At the Department of Mechanical Engineering here at UConn, we apply these advanced derivations every day. We're using them to design the next generation of ultra-efficient, environmentally conscious propulsion systems. If you find these universal laws as fascinating as I do, you'll see they apply far beyond machines. I explore how these principles govern our everyday problems in my upcoming book, The Engineering of Life. It's an engineer's guide to understanding the laws of everyday living. I invite you to pick up a copy when it's published to learn more about how these laws shape our world. Thank you for following along with this technical deep dive. Until then, keep analyzing, keep questioning, and keep engineering. I'm former Professor Ganesh, and I look forward to our next session on quantum mechanical equations. Take care.